Hello there. In this video, we're going to be analyzing RL circuits and using the general solution to natural and step responses to help us formulate an equation for the current through this inductor. Okay? Now notice that we have an RL circuit. We have resistors, we have independent sources, and we have an inductor. Now remember the steps that when we're using the general solution to natural and step responses, we want to find currents through inductors and voltages across capacitors. In this case, since this is a RL circuit, we want to find the current through the inductor. So our XF here will be current. So our variables will be current in terms of currents and in terms of amps. So we want to find when the current, the final current, as time goes to infinity, the initial current minus the final current, e to the minus t over tau. If you recall, in RL circuits, tau, the time constant for RL circuit, is equal to L over R Thevenin's. Okay, and in the beginning equation, we have that the initial current through the inductor is 3 amps. So there's 3 amps already stored in this inductor before we even start analyzing this equation. So we already know that this 3 amps goes into this part, this IL initial. Now, in this video, I'm going to start by using source transformation. As you can see, that if we did node analysis or mesh analysis, we would have 4 node equations and 4 mesh equations. So let's simplify by using source transformation. Okay, now we have this 3 amp current source, in parallel with this resistor. So this is essentially, it looks like Norton's equivalent. Now we have to turn it into Thevenin's equivalence. Okay, that's how we do it. We take part of this circuit, we remove A and B, remove it, and we want to transform it into voltage source in series with the resistor. Okay, our resistor is 4 ohms, and that would stay the same. So using Ohm's law, V equals IR. We have that our Thevenin's, excuse me, Thevenin's, so a voltage source in series with our 4 ohm resistor. The value of the voltage source is, well, the current I times its resistance will give you the voltage part. So 3 times 4 is 12 volts. So you have 12 volts. Okay, now we add back the rest of the circuit. So we have 6 ohms there in series, 6 amp current source, 6 ohm resistor, and this inductor, this 0.4 Henry inductor, and this 12 ohm resistor, and this 12 volt voltage source. Okay. Now these resistors are in series, so we can simplify this by adding them up, and we'll have 4 plus 6 is 10. So we have 10 ohm resistor, and we have this 6 amp current source. We'll put back 6 ohms and put our inductor, 0.4 Henrys, this 12 ohm resistor, and this 12 volt voltage source. Okay. Okay, now that we have our Thevenin's equivalence, transform it back by using source transformation back to its Norton's equivalent. How we do that, we use V equals IR, Ohm's law again, V equals IR. But in this case, we want a current source in parallel with our resistor. So our value for our current source would be V, the voltage divided by the resistance series will give you the value of the current source. So you would have, what is it? We have 12 volts. 12 volts divided by 10 will give you 1.2 volts. Oh, 1.2 amps, excuse me. Amps, sorry. So 1.2 amps as our current source in parallel with our resistor, 10 ohms, 10 ohms, 10 ohm resistor, and now we add back the rest of the circuit. So we have the 6 amp current source, amps current source, the 6 ohm resistor, and this 0.4 Henry inductor, 12 ohms, and our 12 volt voltage source. Okay. Now notice that we have this current source, independent current source, is in parallel with this independent current source. We can add independent current sources in parallel. We can add independent voltage sources in series. Okay. So we have these two independent current sources in parallel. If we add them up, we have this current source going up, the 6 amp going up, and this 1.2 amp going down. So when you add them up, you have 4.8 amps going up. 4.8 amps going up. And we add back our resistor, 10 ohms, and our other resistor, and the rest of the circuit, 6 ohms, 0.4 henries, and 12 ohms, and our voltage source. Okay. Okay. Now look at this. Look at this. We have current source and parallel with our resistor, Norton's equivalence. We got source uses source transformation. We transform it into its Thevenin's equivalence. Still using V equals IR. V equals IR. Our current value is 4.8, and our resistor value will be 10. So when our voltage, our value for our voltage source would be 4.8 times 10, our resistance, it's equal to 48 volts. We have 48 volts, the voltage source. And we have our resistor in series with our voltage source, so it would be 10 and 6 ohms. And our inductor, 12 ohms and 4.4 henries. And our voltage source, okay, 12 volts. Now we have these two resistors in series, so we just add them up and simplify this circuit furthermore. So 10 plus 6, 16 ohms. And this inductor, 0.4 henries. And 12 ohms. And we have our 12 volt voltage source. Okay. And now finally, we have Thevenin's equivalence on both sides. See a voltage source in series with the resistor and a voltage source in series with the resistor on both sides. So let's transform both sides using source transformation into their Norton's equivalence. Okay. Now let's do this. So I'm just do this quickly. So this current source, so it'll be V divided by its resistance. So 48 divided by 16 will give you 3 amps. 3 amps. And you would have your resistor in parallel, right? Divided by 6, so 16 ohms, and this inductor, 0.4 henries, and our 12 ohm resistor, and our current source. Oh, you know what? I just made a mistake. I copied it wrong. Oh, you guys gotta watch out when you're copying it, your circuit. So I messed up. This should be 20 volts. So 20 volts. This should be 20 volts. Sorry, 20 volts. Um, 20 volts. Should be 20 volts. 20 volts. 20 volts. 20 volts. And 20 volts. Okay, so now we have our current source, our current value. So 20 volts divided by our 12 ohm resistor, we give you our current value for our current source, 1.67 amps. 1.67 amps. Okay, now that we need to find, what we're doing is we're finding our final value for our current through our inductor. And this is under steady state. So under steady state, inductors short and capacitors pop open. So this inductor, when t is greater than 0, when t goes to infinity, this inductor will short. So we replace it by a short wire. So we replace this by a short wire. Essentially, we would have a 3 amp current source in parallel with our resistor, 16 ohms. And this will short, right? Our inductor is short under steady state, so 12 ohms. And our current source, 1.67 amps. And notice that we have this short wire. This is our ground wire. This is attached to our ground wire. This ground wire is in parallel with the resistors. Whenever you have your ground wire parallel to your resistor, these resistors are removed. These are removed because they share the same voltage. The voltage across the ground wire is 0. 0 volts, you have 0 current through the resistor. So these 16 ohm resistor and 12 ohm resistor are removed from the circuit because they won't have any current flowing through them, neither voltage across. So we have this current, 3 amps going in. We have this 1.67 amp current going in, and this would be going through our inductor. So if you use Kirchhoff's current law, currents going in equals currents going out. So our I, L infinity is equal to 3 plus 1.67 amps, equal to 4.67 amps. That's our I, L infinity for when this is our current through our inductor when time goes to infinity. Now we have to find our tau. Our tau, so our L, so our inductor 0.4 henries. Now we have to find our Thevenins. Our Thevenins, well, if you look at, remember this, our resistors are in parallel. So 16 ohms plus, in parallel with the 12 ohms. 12 in parallel with the 16 ohms, we have our Thevenins. So that's equal to 6.86 ohms. That's our Thevenins. Now, finally, tau is equal to 0.4 henries divided by our Thevenins, 6.86 ohms, and that would give us 0.0583 seconds. Okay, now all we have to do is plug in all these IL infinity and tau into this equation, our general solution, and our IL, our initial current through the inductor. Okay, now we'll do that quickly. So we have IL of t equal to our final. So it's 4.67 plus 3, our initial, minus our final, 4.67 times e to the minus t over tau, 0.058 seconds. And that's for t greater than 0. And that's how we do it. Thank you for watching.